let me give a little bit of context as to what this ultra effort that we've heard a few times about today is. So NSF and the U.S. Forest Service recently funded a number of exploratory initiatives to look at urban areas from a long-term perspective and from a coupled human natural systems perspective. And in the Boston area, we had 2 ultras funded. We're the only city lucky enough to have 2 groups funded. And so the results I'll be presenting are from the Boston University-led ultra. And there are a few names that are larger than some of the others that you see on this list, and it's an incomplete list. The larger names are people whose work I'll be presenting today, but this project has a large number of collaborators. What I'll be showing today is really the aspects of the project that most closely couple with what's going on here at Harvard, at the LT. So I have one slide that I wanted to show in the way of introduction, since urbanization is not something typically discussed at the LTR meeting. Currently, urban areas comprise a relatively small fraction of the global land area. Something in the neighborhood of 2 to 5% of global land is covered by urban areas. But about half of our global population lives within these areas. And more importantly, at least in the context of the project that we're undertaking, about 67% of global energy is consumed within these areas. And over 70% of CO2 emissions can be attributed to these urban areas. Our current distribution of CO2 observations and greenhouse gas observations across the United States and across the globe have intentionally not been located in these sorts of locations because of the point source effects on the concentrations. And the FluxNet and Ameriflux network efforts have been focused on characterizing background and characterizing exchanges between vegetated, natural, or agricultural systems in the atmosphere. But as we go forward, these urban areas are projected to increase significantly in their spatial extent, increasing about 2.5-fold by the year 2050, and the fraction of the global population living within urban areas is projected to increase to about 70%. So this image that I've shown here is a MODIS image that nicely shows the distribution of vegetation across the globe and the biomes, and shows a relatively homogeneous view of our natural environment. But if we transition and we look at the human side of what's occurring within these same areas, you can see that there's a tremendous amount of human infrastructure and human activities that are occurring in these same areas that we can perceived to be dominated by vegetation. So our Ultra X project is focused on trying to understand how humans, and they're built in natural environments, interact to produce spatially and temporally varied CO2 exchange in a metropolitan region. And we're trying to look at this from both anthropogenic perspective, where we're building emissions estimates, and from a natural perspective, where we're looking at how vegetation structure and function change as we move across an urban to rural gradient, and from a social perspective, where we try to understand what some of the social drivers of the emissions and exchange and vegetation patterns that we see across the landscape are. Within this larger question that's guiding our ultra, we also have a few other key questions that we're working on. In particular, what are the policy and economic and behavioral levers that are controlling this carbon metabolism across the rural gradient, and trying to understand how distributed networks, whether it be the energy distribution network, water, roads, or even social networks and governance networks, influence these patterns of metabolism. And finally, trying to understand how lags, legacies, and feedbacks from past land use are impacting the current metabolism that we're seeing across the landscape. And I should have probably defined this first rather than last, but what I mean by urban metabolism is the flow of energy and material through an urban environment. And we're trying to tackle this question across an urban to rural gradient, where we're looking from Boston to Harvard Forest and Worcester. So this is the same map that Christina showed a moment ago, and this there's a few things I'll point out here. There's a black line that's outlining the coastal area of Massachusetts, and this is the area that's defined as the Boston Metropolitan Statistical Area. This is one definition of what the Boston urban area and area extent is. And you can see the distribution of some key land covers over this. The other category is other urban covers. This means industrial and commercial lands, as well as things like golf courses and ball fields. But these are lands that are heavily influenced in their composition and use by humans. So overlaid on this map are 2 transects, which we established last summer. We established 140 field sites where we measured species composition, presence and absence of ragweed, poison ivy. We measured live and dead biomass. We took soil cores, foliar samples to look at carbon and nitrogen, soil bulk density. These circle points that you see here, in addition to being the location of Harvard Forest and 2 major cities along in this area, are also where we have atmospheric observations in place. We're measuring CO2, methane, and meteorology on the roof of BU. Allison Dunn and I and others just set up a new site in Worcester, and then we're comparing this to observations at the Harvard Forest EMS Tower. One of the questions that we've been working very hard to answer, and my postdocs, Steve Rosidi in particular, has been pondering this deeply, is what is urban? And in our analysis, we have been testing the sensitivity to some of our results to this definition of urban. And the results that I'll show you today are using one definition, but this is an ongoing effort. What is plotted here is the fraction impervious surface cover as a function of distance from the Boston urban core. And you can see a very clear threshold that is present at the Route 95 Beltway. And we drew a line for this first preliminary analysis that I'm going to show you to define urban as areas that have more than 25% impervious surface cover, pavement, within a 1 kilometer square area. And this is something that we're continuing to refine, but this is how the results that I'm going to show you are focused. So in terms of live biomass, what we found in these non-urban, so these are areas that have less than 25% impervious surface within a 1 kilometer grid, we found biomass, we found biomass comparable to what we see here at Harvard Forest. And in urban forests, the biomass was actually comparable to what we found in rural forests. We're still doing the analysis to understand how the species composition changes, but the biomass was not, those error bars are overlapping between what we saw in the urban and the rural forests. You can also see how the amount of live biomass changes as we go to the residential areas and to these other urban areas. And the residential areas actually hold a quite significant amount of carbon because the Boston area was developed in large part a long time ago. And enough time has elapsed where we have large trees with a large fraction of canopy present within this area. If we do a first order scaling with a paint by numbers sort of approach, and we look at how many pixels we have within this area that are this urban versus non-urban with these different land cover classes, we can estimate that in the state of Massachusetts, it's in the neighborhood of 84 megagrams of carbon per hectare. So not that much lower than the 120-ish that we have here at Harvard Forest. And that's because a large fraction of Massachusetts is covered by forests. Within this Boston metropolitan statistical area, this outline that you see here on the map, the number drops to about 72, which isn't that large of a drop. We've also done some work characterizing what the more urban environment looks like at a higher spatial resolution. This map that's shown here is the result of a master's thesis at BU, which is in revision for publication now. And what we did here is we fused QuickBird and LiDAR data along with a number of different inventories that we acquired to be able to estimate at the individual tree scale what the biomass looks like within the city of Boston. And what we found is that the current canopy cover in the city of Boston is about 26% plus or minus 1.5. And this is a number that we can hope, assuming that funding isn't completely cut, that this is a number that we can hope will increase as part of Mayor Menino's Grow Boston Greener efforts to increase this number to 35% and plant another 100,000 trees. Within the city of Boston, the biomass estimates, this is the most the most densely populated, largest fraction impervious area, we still have a biomass of about 28 megagrams of carbon. And these plants are growing in a very different environment where the nitrogen deposition, the soil characteristics, and the CO2 environment is very different. So we can expect that this vegetation will respond differently than the vegetation that we see in the more rural areas. I'll highlight the teal pixels in this map, which are areas that have vegetation carbon stocks that are comparable to what we see here at Harvard Forest. This slide has a lot of information on it, and I won't actually spend a ton of time on it, but this is showing some preliminary results that we have looking at soil chemistry and soil density across the same gradient. And what we found is that the developed lands actually have similar soil carbon to nitrogen ratios, regardless of whether the site was in an urban context or in a rural context. In contrast, the forest and the residential areas had higher soil nitrogen concentrations in the urban areas. And that's likely due to increased deposition, but that's something that we're hoping to establish direct measurements of. The bulk density of the soil also increased in all of these land cover land use classes as we transition from the non-urban to the urban environment. Christina highlighted this a little bit already, but as part of these vegetation surveys, we also looked for the presence and absence of ragweed. And this is a little bit different of a plot than what Christina showed. This is showing how the absence and presence of ragweed was related to the amount of biomass that was present as a function of these different land use categories. And you can see a statistically significant relationship between forests in the urban environment that have a lower amount of biomass versus what you see in the higher biomass areas. And that's likely related to changes in what the light input rates are. Overall, we found ragweed present within 18% of all of our forest plots, urban or non-urban, and then increasing up to 28% within these other urban categories. And as Christina mentioned, we also have one of these Burkhardt traps that's located on the roof of Boston University, and we have planned schemes underway to try to integrate some of this ragweed transport modeling with what we're doing with CO2 modeling. So this is just next to where that Burkhardt collector is located. We have the Eddie Cavarian's tower located on the roof of Boston University. This is the building height is about 30 meters with another 2 meters for the tower location there. And we've been monitoring CO2 concentrations since 2007, and since February of 2010, we set up a Picaro analyzer for monitoring CO2 and methane. This is one slide from a manuscript that will hopefully get submitted this week, which is looking at differences in the CO2 concentration at Harvard Forest and at BU. This is wintertime data that I'm showing here, but you can see that the diurnal concentration pattern looks very different at BU, where you have a very strong stratification and change in the boundary layer height that's occurring, as well as continuous sources. And this is winter data, so there's a lot of heating emissions contributing to the CO2, versus what you're observing at Harvard Forest, which has a much smaller diurnal cycle associated with it. The lighter gray triangles that you can hopefully see there are showing our methane observations on a diurnal cycle. The lower panel is showing the relationship between the concentrations and the mean wind speeds. Overall, over the winter period, this is the period where biological activity is at a minimum, the difference in the CO2 concentration between these two sites is about 12.7 parts per million. And at the Boston University site, we found about a 2 ppm difference between weekday and weekend concentrations. These results are from a Harvard senior who just submitted his thesis a few days ago that Steve Wofsy and I were co-advising, and they came out slightly fuzzy. But what this is showing is that if we look at the time series of these paired observations and what we're seeing at BU and at the EMS tower, this is the morning data versus the afternoon data. And you can see the very clear drawdown in concentrations at Harvard Forest. You can see a similar drawdown that's occurring at BU, which is partially being contributed by a reduction in heating, as well as the vegetation within the urban environment. And we're working on disentangling those two in more detail. And then, during the afternoon, the two observations come much closer together. Finally, since I'm running out of time, I won't spend a ton of time on this. We've also made mobile measurements of atmospheric CO2 concentrations to get a better idea of how the CO2 concentrations are changing across space. These are the results from one of these driving campaigns. We've done 5. We've set up the Picaro analyzer in the trunk of my car and put the inlet out the back of my sunroof and went for a road trip. And you can see some very nice relationships between your orthogonal distance from Boston and your CO2 concentration, clearly highlighting the urban CO2 dome. And this is the northern leg of this map. So this is the part that's going near Route 2 and Route 2A up to Harvard Forest. If we look at the southern leg, which is following Route 9 and closer to Route 90 and is more urban, you see a pretty different signal in what that concentration looks like as a function of distance. And we are working this summer to do some atmospheric transport modeling to couple these point observations that we have at these two sites and get a better estimate of what's happening across space and time that's more resolved. So I'll wrap up by just kind of coming back to what our central question for this project is to try to understand how humans and their built-in natural environments are interacting to produce these spatially and temporally resolved CO2 exchange within the urban metropolitan area. What I've focused on here are the measurements that are coupled to Harvard Forest, but there's many other aspects of this project. The social aspects I haven't really highlighted here. And as we move forward with this and move forward with the full ultra competition, we're going to continue efforts along this metabolism theme, but we're going to integrate other biogeochemical cycles, water, and more explicitly couple the flows between the atmosphere, the terrestrial biosphere, and coastal environments. And Crystal, who's in the audience, is one of the key people leading up this coastal connection, and I think we're going to start making some measurements on that in the coming weeks. And finally, we're going to continue this focus on lags, legacies, and feedbacks, which is something that we've only just scratched the surface on. And there are very clear synergies between what we're doing for this Boston Ultra and other efforts that are underway here at the Harvard Forest, including the Future Scenarios Project, the EPA project, which I've mentioned, as well as trying to look at gradients in ecosystem structure, function, and atmospheric concentrations.
Time for a micro question.
Peter.
I was kind of amazed at your use of 25% impervious paving as a definition of urban.
So we've tried others, but go ahead.
Well, the question is, what's the percentage of impervious paving for Boston? And I mean, it seems to me 25%. That really pushes the limits of an urban area way out. It's almost be an example of a town or a city that's got 25% impervious paving.
So my postdoc, Steve Rossetti, is actually doing a lot of work on this, and I'll point you guys to a poster that he has upstairs, and he'll be able to answer more questions on this. But we've been working very hard, and we've been trying different definitions and looking at the sensitivity of our results. Our samples were actually stratified using a combination of impervious surface, population density, and land cover. But the population density was not an independent variable from what we were seeing with the impervious surface. And we're still working on that definition, but we collected our samples in a way that the analysis is flexible to what exactly that definition is. So I don't know what the right answer is. We're still trying to figure it out.
Thanks. And our next talk is by Robert Ryan.